Now another thing as we see as we look out are binary stars, two stars that revolve around their mutual center of gravity. Binary star systems offer one of the few ways to measure stellar masses, and stellar mass plays a leading role in a star's evolution. At least 40% of all stars known have orbiting companions, some of them more than one. Most binary stars are only a few astronomical units apart, and a few are even close enough to lightly touch. We have different types of binaries we see. The first is a visual binary. They're systems where we can see the orbital motion of the stars around each other by comparing images made several years apart. So I'll usually have a larger star and a smaller star, and they will be rotating around this common center of mass. The next is called a spectroscopic binary. They're too far away or too close together that we can't actually see two stars. But as we look at the spectra, we see that there are two lines and they move apart from each other and towards each other, apart from each other and towards from each other. And so Doppler analysis of the spectra then gives us the star's speed by observing a full cycle of the motion of the orbital period, and then we can determine their distance from each other. Now Newton modified Kepler's third law. The mass of the two stars times the period of revolution is their distance away from each other. And if I know their distance and I know their period, I can determine their masses. P and A are determined from observations, may take several years, and the above equation gives their combined mass. And further observations of the orbit allows the determination of each star's individual mass. What we see is most stars fall in this narrow range of about 10% of our Sun to about 30 times the mass of our Sun. The next kind of binary that we can see is something called an eclipsing binary. These again are stars that are too far away that we can't see two different stars, but I can look at the light coming from it. And when the two stars are side by side, even though we can't resolve them, we're getting light from both of them. And then as the smaller star goes in front of the larger star, it's blocking some of the light, and so it goes dim. Then it comes out from behind and it goes bright again. Now when that smaller star goes behind it, I also lose some lightness, not as much. So now by looking at this distance here in time, I can measure the period of these stars. By actually looking at how much light is blocked off and the ratio, I can actually figure out the ratio of their radii by looking at how much light is blocked off. So the duration and manner in which the combined light curve changes together with its orbital speed allows astronomers to determine the radii of the two eclipsing stars.